Hi, my name is Dana Golden. Welcome back to cost-benefit analysis. We're going to continue with a look at risk valuation, particularly risk valuation in an environmental context. So what is risk valuation? Risk valuation assesses the monetary value of uncertain future outcomes associated with potential environmental changes or hazards. It incorporates probability of risk and the potential impact into decision-making. Most risk evaluation include probability of the likelihood of an adverse event occurring, like flooding or pollution, the adverse effects of flooding and pollution, magnitude, how bad will the damage be, and time horizon. If the risk is long-term, like climate change, you often require discounting the future. So this is difficult because we know climate change will be bad, but there used to be, now there's not that much, but there used to be some debate about how bad and like what the time horizon was going to be. And so we need to think about how to deal with that risk, acknowledging how bad the results can be, but also acknowledging that we used to have some uncertainty. So of course, the expected monetary value is equal to the expectation, which is equal to the probability of event and the cost if the event occurs. You saw something very similar in Lecture 3 last time on imperfect information insurance markets. Willingness to pay to reduce risk to avoid harm is generally greater than or equal to expected monetary value because people don't like risk, and the cost-benefit analysis tries to incorporate these risk factors. So these are three different factors. You can either do cost-benefit analysis and incorporate risk factors. You can do willingness to pay to reduce risk of harm. So you can try and figure out how much people are willing to pay, and you can try to do expected monetary value. What is the expected cost? So returning to last time's flood example from imperfect information insurance markets, we have a flood risk in a coastal area. A coastal town faces annual flooding risk due to climate change. The probability of severe flooding is 5% per year. The estimated damage cost is $1 million. The expected cost of flooding is then the probability of the flood times the cost of flood. This is 0.05 times 1 million. This is also kind of assumed to be plus 0 times 0.95. because it's a 95% chance of paying zero cost. It's $5,000 per year. It's a decision whether or not to invest $200,000 in flood defenses to reduce the P to 1%. So the new expected mean monetary value of damages is 0.01 times 1 million, which is a $10,000 expected monetary value, and then the new net benefit is $50,000 the expected monetary cost minus $10,000 times the number of years minus the initial cost, which is $200,000. So we're thinking about systematically how do we consider the fact that this is just decreasing the risk from $50,000 to $10,000 per year, and how many years is that going to take to be worth $200,000? Another common example of thinking about risk in a systematic way in terms of cost-benefit analysis is the statistical value of human life. This represents the monetary value society places on reducing the risk of death by 1 unit. It is not the intrinsic value of life, but measures. It's a measure using cost-benefit analysis and helps create policies to reduce mortality risk. You can't. So one thing a lot of people will say is, well, isn't a life worth everything? Shouldn't we do whatever we can do to prevent someone from dying? And I'm not unsympathetic to that argument. I'm not unsympathetic that there are remarkable intrinsic values to human lives, and we should treat them as precious. We should do whatever it takes to help everyone. I agree with that. I agree that human life is inherently precious, but the truth is, we live in the real world. We can't spend $1 billion to stop a car accident. We can't spend $1 billion to keep a person on life support. We have to acknowledge that there are costs and benefits. We have to find ways to value an individual life to see, one, what's worth in maybe a courtroom, how much a company should have to pay if it was negligent and that negligence led to the death of an individual, but also how much we should be willing to pay to reduce the risk of death. So if 10,000 people each pay $100 to reduce the risk of death by 1 in 1,000, then the willingness to pay to reduce the small risk of death is 10,000 times 100 equals 1 million. So the idea is 1 in 10,000 is the amount they're reducing their death by. So 10,000 times 100 is 1 million. So they'd be willing to pay 1 million to avoid a certain death. So some applications. It's useful in evaluating environmental regulations, thinking about air quality standards. How much should we be doing to protect people? It's useful for assessing safety improvements. What should the vehicle safety standards be? It's useful for thinking about how to intervene in health costs. How should we determine what resources to put towards protecting individual life in the health domain? It's also very useful in court cases. In the United States, statistical value of human life estimates the range from 5 million to 10 million, depending on the context and methodology. The EPA has a pretty good accessible methodology if you want to check this out. A quick example, a government agency is evaluating a policy to reduce air pollution, which is expected to lower the risk of death by 1 in 10,000 for 100,000 people. The willingness to pay per person is 200,000. The population effect is 100,000 people. You calculate the total willingness to pay is 200,000, which is 200 times the 100,000 people who are affected by this. So 220 million is the total willingness to pay if you consider all the individuals. And then the lives saved by the policy is the population to lower the risk reduction denominator. Here we're using 10,000. We're lowering the risk of death by 1 in 10,000 for 100,000 people. So 100,000 divided by 10,000 equals 10. So the statistical value of human life is 20 million. The total willingness to pay for this policy divided by the lives saved equals 2 million. People are willing to pay each of them $200 to lower the risk of death by 1 in 10,000. There are 100,000 people who are willing to do this. So the government agency, in calculating the ability to do this, calculates the statistical value of human life at 2 million. We're going to leave it right here and join us next time for a look at discounting. Thank you, and I hope you have a great day.